Good. Okay, so can you see my slides?
Yes, we can.
Great. So thanks to Marcus and all of the organizers for this seminar series. As advertised, I'm going to be talking about a project which I call brain breeding, and this is using genetic algorithms to search a portion of the string landscape. So here there's a very nice portrait which I'll share with all of you of Darwin on the left, and as the name suggests, genetic algorithms take inspiration from natural selection to try and solve some optimization problem. So I'll start with an example, fairly simple example to demonstrate this, and then I'll turn to the model of interest with intersecting D6 branes, and it'll describe how you can phrase this in terms of a genetic algorithm, and we'll finish with some preliminary results. This is ongoing work, so some insights into how the genetic algorithm is solving the consistency conditions that are required, and also some statistics once a large enough data set has been collected. Okay, so first with genetic algorithms, this is fairly general. As I mentioned, inspiration from natural selection. You have some population of individuals which are trying to solve some process as measured by, for example, a fitness function or a cost function. And these individuals will be combined in some particular way, and there will be mutations on top of that in such a way that they slowly evolve, if you will, to solve the problem altogether. So you start with some initial random population, however you want to generate this, this initial population, and you'll loop through this sequence of steps, first selecting individuals to do this breeding process. You'll do this in such a way that individuals which are fitter are preferentially selected to breed. This way the beneficial properties of their characteristics are carried over into the next generation. Once you have selected two parents, you can combine their genetic material via crossover, apply small mutations so that not everyone is identical, and add them back into the population and repeat. There's one extra ingredient one can use, and we'll use it later on, which goes by the name of elitism, which is where you take some proportion of your population, which is the fittest, and copy them over into the next generation. So survival of the fittest, and those will ensure that you never are losing your most fit individuals. So you get monotonic progress towards this optimization problem. So just as a toy example of how this works in practice, there's a problem known as the knapsack problem, where you're given a collection of items of different weights and values. And the task is to maximize the value, the total value, given that you have to be below some maximum capacity for your knapsack. So we can phrase this in terms of genetic algorithms. You have individuals which consist of the choice of items to be selected. So we can represent that as zeros and ones here. So there are 5 items. This first individual would select the first, second, and fourth, giving a total weight of 22 and a value of 55. This is over the capacity, so this should be extremely penalized for this violation. And indeed, we can design our fitness function to just give a value of 0. So this is terrible. Individuals which don't go over capacity, we can measure their fitness by the value that they achieve. So here, this individual has 33, but lots of space for adding additional items. This individual actually is the optimal solution. Although they're below the capacity, they have the maximum fitness. So this is a very small example. You could even just brute force this or even do it by hand to find the optimal solution. But how the genetic algorithm would go is you want to select individuals, these strings of zeros and ones, and combine them via crossover. So here's a larger example with 12 items. The 2 chromosomes would be, for example, split at some randomly chosen point, and then spliced together to create a child that's then added back into the population. For mutations, there's a simple obvious choice where you take the bits describing the individual choices and flip it from 0s to 1 or vice versa. And these are applied at random. So what does this look like when we actually run the algorithm? Here's an even bigger example. So 16 different items that could be either included or not included in the knapsack. Still viable to do a brute force solution, but what we'll see is that you can find the optimal solution visiting just a small proportion of all possible states. So it's very efficient. It only searches those regions which are potentially viable. So for this example, I've just fixed a population 50 individuals. 5 of them get copied over without any changes, and some different mutation rates, which can demonstrate some of the pitfalls in this algorithm. So we start with a random population. Almost all of them will be over capacity and will just all have fitness of 0. And we can see that some initial progress is made just in getting below the capacity, still a terrible fitness. The maximum possible is up here at the dotted line. But what we see is if your mutation rate is too slow, or too low, I should say, we go just a little bit further. On the left, with very few mutations, you have your maximum fitness, your best individual, and the average fitness, your typical member of the population, are basically identical. So you have a population of identical individuals. This is not desirable. On the other hand, if your mutation rate is too high, then all of your individuals are too random and they're not making this incremental progress towards the maximal solution. Somewhere in between is a bit better, and indeed we see that the optimal solution is found around generation 12. And even if you continue going, the population as a whole will still be some random individuals, and you could potentially look for other optimal points. In this case, there's only one. Okay, so now let me turn to the model of interest. This is some intersecting brain models in type 2A string theory. Just a bit of history before we get into the model itself. This type of model with intersecting brains is quite desirable because a natural way to have non-abelian gauge groups in the effective theory, 4-dimensional theory. We have a mechanism for arriving at a chiral spectrum and also replicated matter. If you have two stacks of branes that intersect multiple times, you'll have identical matter representations showing up in your spectrum. There are natural mechanisms for having a dark sector as well, so this is quite nice for pheno purposes. In terms of the history, some early models were written down in the early 2000s on this compact geometry. If one looks at a fairly exhaustive search of the space at low integers, which describe the solutions, I'll talk about that in a sec, one can make some estimates about how frequent MSSM-like properties show up in consistent models. So this was in the paper 1 in a billion in the early 2000s. The set of consistency conditions is some very complicated Diophantine equations and inequalities, which in general is NP hard to determine whether, first of all, whether there are solutions, but also whether there are a finite number of solutions. But for this particular set of Diophantine equations, there was a proof of finiteness that followed fairly shortly after. And then more recently, we've seen some modern techniques come to the table. This group here 2 years ago used reinforcement learning to search through the landscape and find these consistent models with lots of success. So what is the model? We have this T6 with the orbifold action given by this theta and omega, not too important for where I'll go from here. We can introduce O6 planes with this orientifold action acting locally as complex conjugation. And there are two different tori shapes. which are compatible with this action. Either you have a rectangular torus or you have one that's tilted at a particular value of the shear. And around each of the cycles of the torus, you have 2 1 cycles, which we'll use to build up the cycles for the D6 branes. So for a particular choice, there are, let's see, 4 different choices for how many tilted tori you have. And then for each of these, you can choose the aspect ratio of the torus as well. So the D6 branes, we can take to wrap 3 cycles on this orbifold, 1 cycles on each of the 2 tori, which are labeled by 2 integers, co-prime integers, n's and m's. So this is some basis using the alphas and the betas, which we can conveniently write in terms of this pi plus and pi minus. These are orientifold even and orientifold odd 3 cycles. And these coefficients x's and y's, which will appear later on, are combinations of winding numbers in these particular ways. So the hats on the m's show up when you have tilted tori. This is a convenient rescaling to be done, which keeps everything to be integers. All of these x's and y's are not independent. You have 8 coefficients showing up, which are derived from just 6 winding numbers. So these are constrained. They satisfy some product relationships and also some coprimality relationships as well. And so what we'll do is when we're applying genetic algorithms to the problem is we'll take the winding numbers themselves to be constituting the chromosomes and also the multiplicity of each of the stacks. The consistency conditions that we want to satisfy, there are 3 of them. One is the absence of RR charge, so tadpole cancellation. There's some negative contribution from the O6 planes that needs to be canceled from the D6 branes. We want to avoid global anomalies, which is measured by this K-theory charge. So this should be even, very compactly written in terms of the x's and the y's. So this is why that basis is so nice. And also we want each of the branes individually to be preserving the same supersymmetries as do the O6 planes. And this amounts to these 2 conditions involving the complex structure moduli. So all told, if we have K stacks of D6 branes, then we have 2K plus 8 Diophantine equations or inequalities in this bottom left case that need to be satisfied. So in general, this is very over-constrained, which indeed is why you eventually have just a finite number of solutions, but it turns out there are lots of solutions. So those are what we're looking for. Our fitness function will choose to be a measure of how well these conditions are being satisfied. And over the generations, the population will evolve to minimize the fitness so that all of these are equalities. Okay, in terms of the pheno, as I mentioned, each of the brane stacks contributes a UN gauge factor generically. And so you can ask, what is the chiral spectrum? So the massless spectrum at this level. And that's given quite simply in terms of the winding numbers as well. So we have bifundamental matter, and it's also replicated because these brane stacks will intersect at multiple points. So one can imagine taking this spectrum and building into the fitness function some properties that are desirable. For example, standard model gauge group having exactly 3 families and so on. There's also a classification that can be done for the different X's and I's derived from the winding numbers. In particular, how many of each are positive, negative, or 0. We break this up into 8 different classes, and only those in the top half, the A, B, and C, can potentially satisfy the SUSY conditions. So you'll notice that the only negative contribution to the tadpole, the X's should add up to 8. The only negative contribution comes from the type A branes, and it's overwhelmed by this positive contribution. So this was crucial in proving that there are only a finite number of solutions. There's also some natural maps which take you from these undesirable branes to those that are healthy and should appear in consistent models. For example, if you take this A prime type and flip the signs of all the winding numbers, that will land you at a type A brane. So they're natural maps that take you from the ABC prime to the ABC. These ones are a bit of an oddball that can't get rid of immediately. So now for the genetic algorithm, there are a few things that need to be specified. Our chromosomes, as I mentioned, will involve these winding numbers and the multiplicities, but we should describe also how they're combined via crossover and what possible mutations will be applied to them. In order to just put everything in a finite box, we'll bound what's the maximum size of the multiplicity, and also we'll put some fairly generous bounds on just how many stacks can be present. What we find is that typically we're looking at solutions which have on the order of 5 or 6 brane stacks. And so we just put Kmax as 10 and it doesn't restrict it too much. But just so that we have something finite to work with. For each of the runs, we'll have fixed complex structure moduli so that each of the individuals is trying to solve the same problem at the same time. This makes the crossover much more efficient. Otherwise, you have 2 individuals which are satisfying different SUSY conditions. Combining them is going to give you nonsense. So we have a consistent problem to be solved across the population, and that amounts to fixing the complex structure moduli. There are a few extra conditions which we have to keep in the back of our mind. These winding numbers need to be co-prime, pairwise co-prime. And so there's some additional checks that need to be done before the child is added back into the population. Based on this classification that I described and using these natural maps, you could even enhance the efficiency of the algorithm by either removing or changing these brain types into the desirable ones or including type C branes automatically. So you can improve the efficiency by making these changes by hand, but we'll see that even without this, we have quite good success. So for the crossover methods, we used 4 different methods. Again, just a 1-point crossover where you split the chromosome at a single point and splice them together to form the chromosome for the child. These differ just in where the split is allowed to occur. So for the first 2 here, you can split them and keep stacks all together. So all the winding numbers that come as a collection all together. Or you can imagine splitting a stack in between 2 winding numbers and splicing it together there. So you get large changes to your chromosome, 2 sets of stacks coming together, or even just a single stack split in half and spliced with another. So why are there 4? The second and the fourth have the additional constraint that the number of stacks matches one of the parents. So this is quite useful, especially later on in the evolution, in the later generations, when you're making more fine-tuned changes and you don't want quite drastic changes where, for example, okay, none that I have are quite drastic, but you can imagine taking a 3-stack solution with an 8-stack solution and combining to give a 5-stack solution that's quite different from the others. So this is maybe not what is desired. For the mutations, so in the knapsack problem, there was a fairly simple operation, just taking 0s to 1s and vice versa. Here we have, again, 4 fairly simple mutations which make very small changes to the chromosome of the child. So one is to take these stack multiplicities and change them just by ±1, or you can take your winding numbers and change them by either ±1 or 2. This ±2 is quite nice because you can jump over the numbers that have a common factor. So for example, if you had 2 and 3 together, having a +1 mutation would get you to 2, 4, which is not co-prime. So you want to somehow jump over that even number and land on 2, 5. So this it's still a small change, right? ±1 or ±2, but it can help avoid those hurdles in the fitness function.
You have 5 more minutes.
Great, thanks. There are also some natural operations on the collections of winding numbers. You can randomize the signs, which has the effect of changing some of the signs of the X's and the Y's, or reordering them in such a way that the X's and Y's get get permuted as well. So these are small changes that keep the population diverse. Our fitness function measures how well the consistency conditions are satisfied. So there's a term for the tadpole, for the K-theory charge, and the SUSY condition. So again, we have this cycling process where you step through the generations and make this, this incremental progress. There are a bunch of parameters that need to be fixed. So if people are interested, I can talk a little bit more about this afterwards, but you have to pick mutation probabilities. You have to pick what are the probabilities for the different crossover methods. You have to choose the weights that show up in your fitness function. So how much are you weighting the tadpole versus the K-theory conditions versus the SUSY conditions. And this will dictate exactly how the population evolves over time and solves the problem at hand. Okay, so now let's get into the results. So in this last 5 minutes, what I'm showing here is a typical run. So you set the algorithm going. You can look at how the population is evolving over the generations. So in this top left is showing just the distribution of the fitnesses. We start with a random population where the fitness is very bad. It's close to its maximum value of 1. And as we go through the generations, this is minimized, and eventually a fully consistent model is found around generation 65 or so. We see that due to the mutations, we still have some randomness in the population, which keeps it not all identical. On the right-hand side is a bit more detail on how this evolution occurs. Left to right is showing the tadpole fitness, so how well that first term is being satisfied. And up to down is showing how well the SUSY condition is being satisfied. We start with a random population where they're both terrible, up at their maximum value of 1. And as we step through, so first 10 generations, then 20, and then 50, we see that first, the SUSY condition is satisfied by this line of individuals here at exactly at 0. There's one individual which has managed to satisfy the tadpole cancellation. And then as we step forward, and indeed only in 10 more generations, we'll eventually get solutions which hit the origin and are fully consistent. And so this final step we can understand actually in terms of this brain classification. I mentioned how type C brains don't affect the SUSY and the K-theory conditions, but they can help to solve the tadpole cancellation. And so we see that types A, B, and C brains become more popular in the population as a whole. And exactly in this, around population 50 is where the type C's brains have proliferated, and eventually they find a convenient combination to satisfy the tadpole as well. So we see this exponential growth and then saturation, and eventually consistent solutions are found around 65, and then we find more as we keep going. Okay, so that's a single run, but you can do this many times, and indeed this is well suited for parallelization. You can do all of the mutations, all the crossover in parallel. You can also run multiple runs in parallel. And so on a cluster, we're able to find on the order of 100,000 consistent models in a few hours. And this is ongoing, so we're hoping to find many more, of course. And with such a data set, you can start to ask questions about the distributions of the pheno properties, in particular the gauge group, on these in these different environments where we fix the tori shapes to be different. So there's this suppression of odd rank when you have untilted tori, which has been noticed before. Unsuppressed odd ranks when you have tilted tori. But we have more. So because we have access not to just fully consistent models, but to those which are slowly satisfying the different consistency conditions, you can ask, how does this distribution change as, for example, the SUSY condition is being satisfied? So these are those models which satisfy tadpole, they satisfy the K-theory, but they have not yet satisfied the SUSY condition. And still work in progress, of course, but the indication seems to be that the distribution of ranks is unaffected whether the SUSY condition is satisfied or not. And let me end here with maybe the most interesting question. If you're looking for the MSSM, you want to have a very particular gauge group, SU3, SU2, U1. And one can ask, what is the distribution? How many models in this data set that we've collected have these particular gauge groups? And also, is the presence of an SU3 correlated with the presence of an SU2 factor? So on the top row here are the distributions themselves. These are the proportion of models which have a particular SUN factor. We see again the suppression of the odd ranks when you have untilted tori, less suppressed or not suppressed at all when you have tilted torus. And on the bottom row is showing the correlation between having two factors, an SUN1 and an SUN2. So generally, these are fairly uncorrelated. Somewhat curiously, this SU2 and SU3 is most correlated. So we'd like to understand this more. Maybe this is a statistical fluke or something to understand further. And you can do the same thing for the tilted tori as well. Okay, so with that, I think I'm just about on time. I talked about genetic algorithms and this simple example of the knapsack problem, showing how the population will evolve. You want to avoid having just identical individuals in your population. You want to avoid having a population which is too random. I described also this intersecting brain model and how you can phrase it in terms of genetic algorithms, this fitness function that needs to be optimized, the different crossover methods and mutations which search through all the possible combinations. There's some indication of how the genetic algorithm is actually learning to solve the three conditions, solving supersymmetry conditions first, and then proliferating the type C brains to try and solve the tadpole afterwards. And I presented some preliminary statistics for the landscape, the gauge group rank, and these SUN correlations. So stay tuned, this is ongoing. We hope to present some more results in the near future. In particular, you could ask what happens if you have more and more tilted tori. The conditions become a bit stronger, but maybe there's less bias in or less suppression in your distributions. You can also ask, how does this change as your complex structure moduli become very large? And you can also, as I mentioned, include terms in your fitness function which bias your genetic algorithm towards MSSM-like solutions. So this is to appear. So with that, let me thank you and welcome any questions.
Thanks a lot for this great talk. So are there any questions from the audience? If yes, please raise your hand and then. Okay, Fabian.
Hey, just a short comment more than a question. So first of all, the Diophantine equation that you get is actually undecidable, and it was a result of Douglas that it has a finite number of solutions, which makes it indeed decidable.
Mm-hmm.
No, it's not NP complete or NP hard. The second comment, so when we did this, we found that, well, somebody else must have found this before, but we couldn't find it in the literature. If you use untilted tori, you can only get an even number of generations. An even number of particle generations. So you will have to twist at least one of the tori. I think you only talked about suppression of the odd gauge groups ranks, but not of
indeed.
Yeah. So you didn't include yet the number of generations.
Yeah, that's correct. So all the results I've presented have no term which favors MSSM-like properties. So you could imagine weighting those which have the correct gauge group, and also the number of generations could be, or families could be built into the fitness function as well. But yeah, that has not been done.
And if I remember correctly, and maybe I don't, there was some problem with getting the coprime thing to work if you had a tilted torus. So sometimes jumping even 2 would not be enough.
Yes, indeed. So yes, good. So that's taken care of in this adjustment phase. So mutations or crossover could lead you to winding numbers which are not co-prime. And then we have some random adjustment where you could, for example, take one of your winding numbers. So you start with 2, 4. You pick one of them and either increment or decrement until it's co-prime. So there is some randomness built into this adjustment phase as well.
Okay, and one last question or comment. So usually people try to avoid elitism because it leads to degeneration of the individuals at large or later evolution, I mean at later generations. Have you tried to lower this or even remove it?
Yeah, so if you remove the elitism, then you don't have this monotonic progress. And so we found that it didn't work as well. Yeah, so maybe that would be interesting. I haven't adjusted it too much. It's usually just been fixed at about 5 or 10%. But maybe something to try would be, once you find a consistent model, reduce the elitism so that you don't just have identical individuals again, and see how that works. That's an interesting idea.
This tends to get you stuck in the
maybe we should leave some more time. So one quick question, maybe from Anindita.
Hi, thanks. So what is the general takeaway from the correlation between N1 and N2 that you got in the second last slide? Did you notice any general pattern?
Yeah, so I would say no, at least by eye. Seems not to be any general pattern. They're weakly correlated, and yeah, I'm not sure I can say much more. Just weakly correlated, but this interesting hotspot here at SU2, SU3 seems to be interesting. So whether that's a real feature or just something that happened to happen, I'm not sure. Does that answer your question?
Yeah, thank you.
Okay, thanks.
Okay, so in the interest of time, let's thank Gregory again